27, runway 8 kilo, you're clear for... This is your captain speaking.
A picture from Sky 6, which is sort of making...
To fully understand the sequence of events that led to the loss of Fine Air, Flight 101, one must first establish a comprehensive baseline of the operational environment, the machinery involved, the human elements at play, and the regulatory framework existing in 1997. This section provides an exhaustive examination of the aircraft, the airline, the crew, the cargo, and the atmospheric conditions surrounding the flight. The intent is to reconstruct the pre-flight reality with technical precision, avoiding speculation and adhering strictly to the findings documented in the National Transportation Safety Board, NTSB, Aircraft Accident Report AAR-99/02. Fine Air was a Miami-based cargo carrier operating under Part 121 of the Federal Aviation Regulations, FARs, which governs scheduled air carriers. Established in the early 1990s, the Fine Air operated within a rapidly expanding sector of the aviation industry, ad hoc and contract cargo transportation. During this period, the demand for rapid freight movement, particularly between the United States and Latin America, saw significant growth. Miami International Airport.
Thank you for waiting, ladies and gentlemen. We've invited first class. Now we're inviting executive platinum, platinum, emerald, sapphire, and ruby if those words are written on your boarding card.
Fine Air's business model relied on the operation of older, fuel-efficient airframes that had been retired from passenger service and converted for freight use. The airline did not own a large fleet, rather it managed a small number of aircraft, often leased or acquired secondhand, to fulfill specific cargo contracts. In 1997, the regulatory oversight of such carriers was undergoing scrutiny. While Part 121 operators were subject to rigorous maintenance and operational standards, the use of aging aircraft, and the pressure to maintain tight turnaround times in a competitive market created an environment where procedural adherence could sometimes be compromised. The NTSB investigation later highlighted that Fine Air had a history of maintenance discrepancies and that the FAA had issued various notices of violation to the airline prior to the accident, though none were directly linked to weight and balance procedures at the time of the crash. Understanding this corporate backdrop is essential, as it sets the stage for the operational culture in which Flight 101 was prepared. The aircraft, Douglas DC 8-6-1F. Bearing the registration number N27UA, the DC-8 family, originally designed by the Douglas Aircraft Company in the late 1950s, was one of the seminal jet airliners that defined the early era of commercial aviation. The 60 series, introduced in the mid-1960s, represented a stretched variant of the original design, intended to maximize passenger or cargo capacity. The -61 model specifically was optimized for short to medium range operations with high-density configurations. By 1997, the DC-8 was no longer in production, and most airframes had been retired from passenger service due to noise regulations and fuel efficiency concerns. However, the type found a second life in the cargo sector. The F designation in DC 861F indicates a freighter configuration. N27UA had been converted from a passenger layout to a full cargo configuration, involving the removal of all passenger amenities, the reinforcement of the floor structure to handle concentrated cargo loads, allowed for the loading of standard aircraft pallets and containers. The aircraft was powered by 4 Pratt & Whitney JT 3D7 turbofan engines, mounted on pylons beneath the wings. These engines, while older technology by 1997 standards, were known for their reliability when properly maintained. The DC-861F had a maximum takeoff weight, MTOW, of approximately 350,000 pounds, though operational weights varied based on fuel load and cargo. There was no fly-by-wire technology. Pilot inputs were physically transmitted to the control surfaces, meaning the feel of the aircraft was direct and unmediated by computer algorithms. Crucially, the DC-8 center of gravity, CG envelope, was relatively narrow, particularly in the aft limit. The aircraft's stability depended heavily on the precise distribution of weight along the fuselage. The cargo floor was equipped with a system of rollers, locks, and tie-down rings designed to secure pallets in specific positions. Each position had a defined maximum weight limit, and the cumulative effect of these loads determined the aircraft's CG. So as the flight manual provided detailed charts and calculations that the loadmaster and flight crew were required to use to verify that the loaded aircraft fell within the certified envelope before departure. N-27UA had accumulated significant flight hours prior to the accident, having served various operators in both passenger and cargo roles. With no outstanding mechanical discrepancies that would have precluded operation. The crew, qualifications, roles, and experience. The flight crew consisted of 4 individuals, each holding specific certifications required for Part 121 cargo operations under U.S. regulations. Their backgrounds, while distinct, shared a common thread of experience within the aviation industry, though the specific depth of their training on the DC-8 type varied. The captain was Hamilton Butler. He held an airline transport pilot, ATP, certificate with ratings for the DC-8 and other aircraft types. At the time of the accident, Captain Butler had accumulated approximately 13,000 total flight hours, with roughly 2,000 hours specifically in the DC-8. According to NTSB records, he was considered current and qualified for the flight. The captain's role encompassed final authority for the operation, safety, and navigation of the aircraft. In the DC-8 cockpit, the captain sat in the left seat and was responsible for the final verification of the weight and balance documentation provided by the loadmaster. Although reliance on ground personnel for these calculations,
Flight 527, runway 8 kilo.
the first officer was Ricardo Bolanos. He held a commercial pilot certificate with appropriate instrument and multi-engine ratings. His total flight time was approximately 4,500 hours, with a significant portion accrued in regional and cargo operations. He was qualified as a second-in-command on the DC-8. The first officer's duties included assisting the captain with flight management, communications, and systems monitoring. In the event of an emergency, the first officer was trained to assume control if the captain became incapacitated, though in normal operations, the Division of Labor followed standard cockpit resource management, CRM, protocols. The flight engineer was Edgar Diaz. On older aircraft like the DC-8, a third crew member was required to manage complex systems that were not automated. The flight engineer held a flight engineer certificate with ratings for turbojet-powered aircraft. His station was located on the right side of the cockpit, facing a panel of gauges, switches, and levers, dedicated to fuel management, electrical systems, pressurization, and engine performance. His role was critical during takeoff and landing phases, where he monitored engine parameters and called out any deviations from normal limits. He also assisted in performance calculations, though the primary weight and balance data originated from the loadmaster. The fourth crew member was the loadmaster, Enrique Nunes. The loadmaster is a specialized ground/flight crew position responsible for the supervision of cargo loading, securing, and weight distribution. Unlike the flight crew, the loadmaster does not hold a pilot certificate, but must be trained and qualified in aircraft-specific loading procedures, tie-down mechanics, and hazardous materials handling. Mr. Nunes was employed by Fine Air and was assigned to Flight 101 to oversee the loading process at Miami. His responsibilities included ensuring that cargo pallets were placed in the correct positions, that weight limits per floor section were not exceeded, and that all cargo was properly restrained using nets, straps, and locks. Crucially, he was responsible for generating the load sheet, a document detailing the weight of each pallet, its position, and the resulting center of gravity, CG, of the aircraft. This document is legally required to be signed by the loadmaster and verified by the captain before departure.
Ladies and gentlemen, good afternoon.
If the data is incorrect, the flight crew has no way of knowing the aircraft is out of limits until they attempt to fly it. Flight 101 was carrying a shipment of textile goods, specifically denim jeans, consigned for delivery to the Dominican Republic, that transpired on August 7, 1997, from the moment cargo loading commenced until the final catastrophic moments of Fine Air Flight 101. This section provides a granular, minute-by-minute reconstruction of the loading process, the pre-flight briefing, the taxi to the runway, the takeoff roll, and the 15 seconds of flight that ended in disaster. Air traffic control transcripts and physical evidence recovered from the crash site. Fine Air Flight 101 was scheduled for departure in the early afternoon. The cargo destined for the flight began arriving at Miami International Airport's cargo apron several hours before the planned departure time. The textile shipment, comprising multiple pallets of denim jeans, operated by a third-party freight forwarder. Each pallet had been assembled, shrink-wrapped, and labeled with routing information. According to standard practice, the freight forwarder provided a manifest listing the estimated weights of each pallet. However, these weights were based on shipper declarations rather than individual pallet weighing, a practice that, while common, introduced the first potential point of error. Upon arrival at the airport, the pallets were staged in a holding area adjacent to the aircraft parking position. The Douglas DC-861F, registration N27UA, was positioned on the ramp.
The captain speaking. Just about ready to depart. We should be away on schedule in the next couple of minutes or so. Flight time will be 9 hours and 40 minutes. We'll eventually reach.
Reported to the aircraft and began coordinating with the ground handling personnel responsible for physically moving the pallets from the staging area into the aircraft's cargo hold. The DC-861F's cargo compartment was accessed via the large forward side cargo door. The interior floor was equipped with a roller system and restraint fittings designed to accommodate standard aviation pallets. The aircraft's cargo positions were designated by station numbers, which corresponded to specific locations along the longitudinal axis of the fuselage. And the cumulative positioning of all pallets
A cruising altitude of 35,000 feet.
1 began approximately 2 hours before the scheduled departure time. Ground crew members used motorized loaders to lift each pallet to the level of the cargo door, after which the pallets were rolled into the aircraft and positioned by hand using the floor roller system. The loadmaster supervised this process, directing the placement of each pallet according to his understanding of the aircraft's balance requirements. According to the NTSB investigation, the critical error occurred during this phase. The loadmaster, Mr. Nunez, did not have access to a calibrated scale to individually weigh each pallet as it was loaded. Instead, he relied on the estimated weights provided by the freight forwarder. The positioning of the pallets within the aircraft was not consistent with proper weight and balance procedures for the DC-861F. The investigation revealed that the majority of the cargo was loaded in the aft cargo compartments, specifically positions located well behind the aircraft's aft center of gravity limit. Percentage of the mean aerodynamic chord, MAC, expressed in inches aft of the datum line, a fixed reference point on the aircraft. The aft limit was approximately 33% MAC. The actual CG, as later calculated by investigators using the recovered cargo distribution and weights.
To give you a smooth flight over turbulence is always a possibility, and for that reason
back on the control yoke to raise the nose and lift the aircraft off the runway, an aft CG condition can cause the nose to rise more rapidly and more steeply than intended, potentially exceeding the critical angle of attack and inducing an aerodynamic stall. The loadmaster completed the loading process and prepared the load sheet, thus the official document detailing the cargo weights, positions, and calculated CG. The NTSB investigation found that the load sheet prepared by Mr. Nunez contained significant errors. The weights listed for several pallets were underestimated, Captain Butler acknowledged the clearance.
It's company policy to recommend that you keep your latch strap securely fastened throughout the flight and visible to the cabin crew.
Checklist, which included final verification of flight controls, configuration settings, flaps and slats extended for takeoff, and briefing of the takeoff procedure. The first officer, Ricardo Bolanos, read the checklist items aloud, and each crew member responded with confirmations.
Flight 527, runway A kilo, you're clear for takeoff.
As the aircraft approached the runway hold short line, the crew contacted Miami Tower. The tower controller provided the takeoff clearance. Tower. Captain Butler. Cleared for takeoff, runway 27 left. Fine Air 101. This exchange was routine and professional. There was no indication of concern or hesitation in the crew's voice. The aircraft taxied onto the runway and aligned with the center line. The crew advanced the throttles to take off power. The takeoff roll, 14:32 to 14:32, 45 Eastern Daylight Time. At 14:32, the 4 Pratt & Whitney JT 3D7 engines spooled up to maximum takeoff thrust. The first officer called out the airspeed as the aircraft passed through specific milestones. First officer, 80 knots. Captain, check. This call-out confirmed that both pilots' airspeed indicators were in agreement and that the acceleration was proceeding as expected. The crew continued monitoring the instruments. The flight data recorder, FDR, which was recovered and analyzed after the accident, confirmed that the aircraft's acceleration profile was consistent with its weight and thrust setting. As the aircraft approached rotation speed, the first officer called out, "First officer, V1, is the critical decision speed. Beyond this point, the crew is committed to the takeoff. There is insufficient runway remaining to safely abort." The captain did not respond verbally, as is standard. The call-out is informational, and the captain's acknowledgement is implicit in continuing the takeoff. Seconds later, first officer, rotate. At this call-out, Captain Butler smoothly pulled back on the control yoke, initiating the rotation maneuver. This is the point where the nose of the aircraft is raised to increase the angle of attack of the wings, generating the lift necessary to become airborne. Under normal conditions, the pilot applies a measured, gradual input, and the aircraft responds predictably, lifting off the runway at a nose-up attitude of approximately 10 to 12 degrees. But Flight 101 did not respond normally. 14:32, 35 Eastern Daylight Time, the uncontrolled pitch-up. As Captain Butler applied back pressure to the yoke, the nose of the aircraft rose, but it rose far too quickly and far too steeply. Within 2 seconds of initiating rotation, the pitch attitude reached 20 degrees nose up. This was double the expected attitude and well beyond the safe range for a heavily loaded aircraft at low airspeed. The aft center of gravity condition meant that the aircraft's aerodynamic balance was fundamentally altered. The tailplane, which normally provides downforce to balance the aircraft's pitch, was less effective. The aircraft's natural pitch stability was degraded. When the captain pulled back on the yoke, the nose rotated upward with much greater sensitivity than he anticipated. The flight data recorder captured the pitch rate, which was abnormally high, 14:32:37, Eastern Daylight Time, stall warning activation. At approximately 14:32:37, the aircraft's stall warning system activated. On the DC-8, this system consists of a stick shaker, a motor attached to the control yoke that vibrates it violently to alert the pilot that the aircraft is approaching an aerodynamic stall. The stall warning activates when the angle of attack exceeds a predetermined threshold, indicating that the wings are no longer generating sufficient lift and are on the verge of losing airflow adhesion. The cockpit voice recorder captured the sound of the stick shaker, a loud, rapid chattering noise. Almost simultaneously, the first officer called out, "First officer, stall." Captain Butler, recognizing the immediate danger, reacted instinctively by pushing the yoke forward, attempting to lower the nose and reduce the angle of attack. This is the correct response to a stall warning: reduce pitch, increase airspeed, and restore lift. The aircraft was traveling at a ground speed of approximately 150 knots and descending at over 2,000 feet per minute. The fuselage broke apart on impact, and the fuel tanks ruptured, releasing thousands of gallons of jet fuel. A massive fireball erupted as the fuel ignited. The aircraft's 4 engines separated from the wing mounts and were thrown forward by the momentum. The crash of Fine Air Flight 101 on August 7, 1997, resulted in the immediate loss of 5 lives, the destruction of a commercial aircraft, and the end of a cargo airline's operations. But the impact of the accident extended far beyond that single tragic day in Miami. The investigation's findings, the safety recommendations issued by the National Transportation Safety Board, and the industry's response to those recommendations catalyzed significant changes in how cargo operations are conducted, how loadmasters are trained, how regulatory oversight is executed, and how the aviation community approaches the critical discipline of weight and balance management. This final section provides a comprehensive examination of the accident's aftermath, the regulatory and procedural reforms that followed, the long-term lessons learned, the memorialization of the victims, and the current state of cargo aviation safety as it relates to weight and balance operations. The analysis concludes with a reflection on the enduring significance of Fine Air Flight 101 in the broader context of aviation safety evolution. Gravity condition causes loss of control, the human factors that led to the loading error, the organizational and regulatory failures that allowed the error to reach the point of catastrophe, and the systemic changes that have made cargo aviation safer. The story of Fine Air Flight 101 is a tragedy, but it is also a testament to the power of learning and the resilience of the safety system. The victims are remembered not only for the lives they lived, but for the lives their loss has saved. In aviation, we remember the past to prevent the future. We study accidents not to assign blame, but to understand causation. We implement reforms not to punish, but to protect. This is the ethic that has made aviation the safest form of travel in human history. Fine Air Flight 101 will remain a case study, a teaching tool, and a reminder for generations of aviation professionals to come. May its lessons never be forgotten.